Okay, let's look at 7.3, modeling data using exponential functions. You'll find this on page 454 of your textbook. So we're just going to go to the need to know section that's on page 460 of your text. All right, so on page 460. So graphing technology can be used to create a scatter plot. That's just your second function. Y equals to just hit on, and then it'll show you little dots. So if the scatter plot looks like an exponential function, then you can use an exponential regression, which is thus an equation, to determine the model for the data. So if it's asking for the model, it's really asking for the equation of that graph. Okay? An exponential function models growth when it's increasing. So if you're on your axes and your graph is increasing, then you know b is greater than 1. If your graph is on a decay, so we know when b is a fraction or a decimal, we're on a decreasing graph, so the slope is going downward. Okay, so we're showing it as a decay. Okay, so you need to know if it's a growth or decay, and you need to know the word model. So exponential regression, like we learned from last video, is just y equals a in brackets b raised to the power of x, or if b is greater than 1, or b is a fraction. Okay, so you're going to be given a chart of data, you're going to enter it into the graphing calculator. From there, you're going to get the model or the equation, and then you're going to use the equation in the second part of a question to answer a question based on the data. Okay, so if you're going to go to example 1, which is found on page 455 of your textbook. So it says the population of Canada from 1871 to 1971 is shown on the table below. Third column, values have been rounded. Okay, so the first column is the time, so that's your independent. Your third column is your dependent, which is your population. So what you need to do in this question, because it doesn't work if you put in the years, is you need to number them as 1, 2, 3, etc. Okay, so in 1871, this will be your first time period. 1881 will be your second, 91 will be your third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and 11th. Okay, so you're going to enter that in the graphing calculator with your population. So if you go to the graphing calculator, you're going to go to Stat, you're going to go to Edit, and you're just going to hit Enter. So I already put all the data in, okay, just to make it easier for me for my example. So I take my data and I'm going to create a scatter plot. So I go to second function y, and my scatter plot, I'm going to hit Enter on 1, and it's already on, so, but if it's not, just hit Enter when it's blinking on. And then I can go to my graph. I'll go to my window, my zoom first, and I'll just hit zoom 6 to make it standard. And then I'll go to my graph and I'll look, it looks like an increase in growth, right? So it's a growth exponential function. Then I'm going to try to find my equation. So I go back to Stat and I move over to Calculate, and I'm going to go find something called EXP-REG, which stands for exponential regression. Okay, so EXP-REG, I'm going to hit Enter. From there, if you're on TI-83, just hit Enter again. If you're on a newer one, go to Calculate and hit Enter. Calculator's thinking, and it gives you an equation. So your equation for this graph is y equals 2.14 in brackets, b is 1.24 raised to the power of x. So if I take this back to here, I'm just going to write the equation here as y equals 2.14 and 1.24 raised to the power of x. Now I know we talked about keeping enough decimal places, so you do want to keep enough decimal places. Okay? So next thing we do, we go and read part B, which is answering a question, but you need the exponential function. So assuming that the population growth continued at the same rate into 2011, estimate the population in 2011. Round your answer to the nearest million. Well, you need to figure out what X would be, right, in 2011. So 1971, we're at 11. So 1981 would be 12, right? So 81 would be 12. 91 would be 13. 2001 would be 14. And 11 would be 15. Okay? So if you go into your calculator, okay, so we're going to go back to our calculator. We're going to take this equation and we're going to put it into our y equals. So y equals 2.14 bracket, or pardon me, let's go times bracket of 1.24 end bracket, use your little hat, raised to the power of x, and hit graph. And it should show you your graph for this exponential function, and it should go through your scatter plot, roughly. Okay. From there, you can then go and hit second function trace, and you can put your value in. You want the value of 15, and hit enter. No, it's not in the range of data. So I got to go back to my window, and I got to change my window. So my minimum for my window would be 0 for x, and at least I need 15, so let's make it 18. Use a 1 for each. My y value is not going to be negative, so my y is between 2 and, I don't know, 60. Let's make it a 5. And let's go back to the graph and let it graph. And then I'm going to go second function trace to get the value and hit enter on the value. I'm going to put my 15 in and hit enter. And my y value is 53.92. So if I go back to my question and I write 53.92, 53.92, and I want to round to the nearest million, so to be 54 million. So it's estimated that in 2011, Canada's population would be 54 million people. Okay, let's look at example number 2 on page 4. Well, actually, it starts on page 457. Sonia did an experiment to determine the cooling curve for water. She placed the same volume of hot water in 3 identical cups, then she recorded the temperature of the water of each cup as it cooled over time. Her data in the 3 trials is given as follows. So you're going to construct a scatter plot to display the data, determine the equation of the exponential regression function, and model Sonia's data. So let's just use trial 1, just for an example anyway. So you're going to go to the calculator, you're going to hit stat, you're going to go into edit, and then you're going to clear the list. So you go to the top where it says L1, hit clear, and then hit down. And then go to L2, hit clear, and hit down. Always make sure you clear your list before you enter new data. Okay? So time is always going to be L1 because it's your independent. So let's just use the 0, the 5, the 10, 20, 30, and 40 of trial number 1. And then the temperatures were 80, 69, 61, 45, 34, and 26. So notice that obviously the water's cooling, right? So notice that you should get a curve that is a exponential decay because your values are decreasing. So you know your y value should be between 0 and 1 on your exponential regression equation, right? So if we go to second function y, we're going to plot our data on our scatter plot. We're going to go to y, and we're going to wipe out this equation from the previous example. And if we go to our graph, we won't see anything. So you're going to have to hit zoom and then zoom 6, which brings it to the axes where 0, 0 is in the middle. And if you go to the graph, you still don't see the curve for the water. Second function, go to plot is on, enter. Okay, so let's look at our window then, change our window here. So our minimum temperature, our minimum x is 0, our maximum x is 50 for our water. Let's put that as a scale of 5, and we can see it on the graph. Our y is our temperature, so our y temperature, maybe let's put it at 10, and then our highest was 80. Let's put 85. Let's put this at a 5, roughly. Okay, and if you go back to graph, you can actually see the scatter plot now. Okay, so you know it's a decreasing function. It almost looks linear, but it is an exponential growth, or pardon me, decay, because it will start to peter off. Okay, so now let's go to the regression. So if you go back to stat and you move over to calculate, if you hit the up arrow, it's a lot easier to find the exponential regression. So you find it, you hit enter, you'll hit enter again to get the equation, and the equation for this one is y equals 79.89, then b in brackets 0.97 raised to the power of x. So let's go write that on for part A. Okay. So y equals 79.98 or 89 in brackets 0.97 raised to the power of x. Okay. So B says estimate the temperature of the water 15 minutes after the experiment, round to the nearest degree. So 15 minutes after the experiment, we know we can just go in here. We can now go into y equals and type our equation, 0.89 times, then the brackets, 0.97, and bracket raised to the power of x. Okay, so I know right away it's a decay because this is between 0 and 1, right? So I go to graph the function, and it shows my linear graph that should go through most of my scatter points. And then once it's done, I want to go to second function trace, and I want to solve for the value when x is at 15 minutes. What's the temperature of the water? It's 51 degrees Celsius because it's said to round to the nearest degree, right? So 51 degrees Celsius for B. And C says, estimate when the water reaches a temperature of 30 degrees Celsius. Round your answer to the nearest minute. Okay, so now we're looking at what? We're looking at taking the equation and actually solving for the x or exponential value with it. Since we're in applied, we're actually not going to use the equation to solve for an exponential because we don't know how to bring x down. So what you can do is go back to your trusty graphing calculator and think, well, y equals 30, right? So 30 degrees, we want an intersect of this line and a constant of 30. So if I go to y equals, and I go down to y2, and I just type the number 30 in, and I go to graph it, I get a line across at 30. So where this intersect occurs is where I can actually solve for my, at 30 degrees, what time is that at? So if I go on my line and I go all the way across, I can roughly guesstimate about 32, right? But if you want to do it correctly, you can go second function trace, and you can actually find the intersect of the line. Okay, so I go to 5, I go to intersect, I hit enter. I want to hit my first curve is my blue curve. If I just hit enter to accept it, and my second curve is my red one, I hit enter to accept it. And it does a guess thing, just hit enter through that. Again, and it's thinking. And my calculator froze again. So it's about 33 or 34. So it's about 33 if you look in the book. So we'll go back to the question and we'll say at about 34 minutes. It'll be at 30 degrees Celsius. And that's it for exponential functions. The next 2 units we're going to look at are logarithmic functions, and then you're done the course. So questions you want to practice on are page 461, question 3, 6, 9, 11, and 13.